Okay, so it's a brand new distribution. What I want to do to start with is just think, what distributions have we come across so far in this, or in S1? What probability distributions have we come across so far? Give me one.
Geometric.
The geometric distribution, okay? Geometric, Nathan, discrete or continuous? Geometric distribution.
Discrete.
Correct, okay? So, can somebody else give me a different distribution? Binomial, discrete or continuous? Discrete. Another distribution, somebody different. Mr. Hawkes, another distribution? Normal distribution, discrete or continuous? Continuous, okay? It's another one we have done. We did it in the continuous random variables chapter. Uniform distribution, and it is continuous, yeah, it's in the continuous random variable chapter. We're now looking at a Poisson distribution, but we are starting just by recapping the binomial distribution. When did we use, there's no need to write this down, when did we use the binomial distribution? What were the conditions that we chose to use it?
Set number of trials.
Set number of trials, yep. What else do we have to have? Constant probability of success, yep, okay. So fixed number of independent trials, with independence that's important as well, each with a constant probability of success, either success or failure each time. Okay, the new scenario that we're looking at is this one here, sorry, go back here, put in the normal distribution. The normal distribution, when was that one used then? And what sort of things would be modelled by a normal distribution?
A lot of things in nature, so height.
Yeah, lots of things in nature, height, things like that, okay? So we got the continuous measurements with the distribution that follows the bell curve, ideal for measurement of length of any natural phenomenon, okay? So the new scenario we're dealing with here, so could you write this line down please in your notes, this red line here? For the Poisson distribution, it's used when we're modelling events that happen at random over a fixed time period or a fixed amount of space. So, used for modelling events that happen at random over a fixed time or a fixed space. So maybe you know the number of cars that pass your front door happens to be, on average, it's, 10 every 5 minutes or something like that. If it's on average it happens so many times per 5 minutes or per 10 minutes, then that is what we have here. Okay, so there are some examples, some famous examples, and things you need to be aware of. One is the number of radioactive particles being emitted from a source in a 60-second time period. No need to write this down, it will be on your handout later on. But there we go, radioactive particles are emitted at random periods, but they will follow on average a certain number per 60 seconds or something like that. Another example, cars passing an observer. Something else that happens on average, you would get the same number of red cars in, for example, a 10-minute period. So those are both time periods. This next one is about a space measurement, like an area measurement. The number of meteorite hits for a 100-kilometre area. So that's a bit here that refers to a space. Number the one we've got here, the number of people fracturing their hips in a week-long period. The hospital may be collecting that data, and they know that on average it's the same sort of thing. So, discrete or continuous? Poisson, looking at those examples, is it going to be discrete or is it going to be continuous? Discrete. It's the number of times it happens. That will be discrete. It will be 0, 1, 2, 3, 4 and so on. So yeah, if we can make a note then, you needn't write all of that down, but if you can make a note that it is a discrete distribution, it's a discrete distribution. Okay, the other things we've more or less got, and it will be on the handout anyway, but just really emphasise the point to yourself, it's discrete. You will get this on your handout later on. But you do need to learn the conditions, just like you need to learn the conditions for the other one. So, okay, the conditions are coming up here. If you could write the conditions down. The first condition is, the events you're looking at occur at random at a constant rate. The events occur at random at a constant rate. So in an A-level question, if it says use a suitable distribution explaining the reason for your choice. You must always write down, I have chosen this because the events, whatever they are occurring at random at a constant rate, and they are independent. So that's another condition. Just like for the binomial earlier, the events are independent. And the key difference between this one and the binomial is this down here. There's no condition about a fixed number of trials. So if you imagine the number of red cars passing you by in a 10-minute period, there's actually no upper limit here. But the probability of 10,000 red cars going past the Kings of Wessex gates in a 10-minute period is going to be absolutely tiny. So the probabilities get so small they're effectively zero. But you don't actually have a fixed upper limit. So when you looked at the binomial distribution, what were the two parameters of the binomial distribution? And what letters did we use? What notation did we use for those? N and P. Yeah, okay. For the normal distribution, what did we use, Joe, for the normal distribution? What were our parameters?
I mean, the variance.
Yeah, mu sigma squared, that's right, okay. For the Poisson, well, we've just recapped so far this bit here on the binomial and the normal. For the Poisson, have a little think. What's the crucial thing, do you think, for the Poisson? Look back at the conditions, maybe. What do you think might be the
rate?
The rate, yeah, that is it, okay. The only parameter for the Poisson is the rate at which the events occur, and we denote that by the Greek letter lambda. Okay. So it's just one parameter. We refer to it as lambda, and it is the mean rate. So it might be 10 per 5 minutes, or it might be 0.2 per square kilometre. Why is the Poisson distribution called the Poisson distribution?
Named after a mathematician called Poisson?
Yes, named after a mathematician called Poisson. Okay, there he is. So basically named after Mr. Fish, who found it in the 17 to 1800s, French mathematician. Okay, that is why it is named the Poisson distribution. Its shape. Now, there's one sort of bad thing about the drawing here. It's not a continuous distribution, so it shouldn't really have any sort of curve there. Really, it is a series of bars going up to these dots. Okay, but it does just show you here the shape you get. When lambda is 1, how could you describe that red distribution? What one word maybe could you use to describe that red shape of a distribution? Think of a word beginning with S. SK. SK.
Skewed.
Skewed, yeah, skewed. That's right, okay. Very skewed, very not symmetric, very skewed. Does this have positive or negative skew? Did you do that in S1? Should have done. Is that positive or negative skew on the red one here? Sorry?
Positive.
Positive, it is positive, yeah. The tail is sort of pointing it out in the positive direction. Positive skew. When you've got lambda equals 4, which is the green one, it's still skewed, but not as skewed. What do you notice when lambda equals 10? It's not particularly skewed.
Looks a bit like the normal distribution.
Looks a bit like the normal distribution, except it's discrete, yeah. But then if you join the top of those bars that should be drawn in there, that does look pretty normal. And we will, fairly unsurprisingly later on, be able to approximate some of these probabilities using the normal distribution, okay, as long as lambda is sufficiently big, and we'll look at how big lambda is later on. So, whole page here of examples of different things that it can be used in. So some of these we've seen before, some of these we haven't. The number of cars that pass through a certain point on a road. Why does it say sufficiently distant from traffic lights?
Otherwise they're not independent events.
Yeah, otherwise they're not independent. It would probably have bunching, I think. So that's something there.
Mess up the rate as well.
Sorry?
Wouldn't that mess up the rate as well?
It could do, yes. It wouldn't be. Well, it wouldn't be a constant rate. It might be, yeah, different after the traffic lights have changed. The number of spelling mistakes one makes when typing a single page. You might know that in so many words or so many pages of text, you average, 3 spelling mistakes. Well, that is a rate, per page. So that would fit as well. The number of phone calls coming into a call centre per minute, they will know that, and it may be different at different types of day. They might analyse it per hour or something like this and know that on a Monday at 9 o'clock it's quite busy, Monday 3 o'clock in the afternoon not so busy, but they may have this rate for different hours of the week. The number of times a web server is accessed per minute, there's an example there. Here's a favourite one of some people. The number of roadkill found per length of road has been found to be distributed in Poisson. 3 dead badgers per kilometre on a Somerset road or something like that, for example. Okay, it's a nice cheerful one. The number of mutations in a given stretch of DNA after a certain amount of radiation has been applied. It's so much per... I don't know what you measure stretches of DNA in. What would you measure stretches of DNA in? Nanometers. That sounds so good to me. The number of pine trees per unit area of a mixed forest. Again, that's an area rate rather than a time rate. The number of stars in a given volume of space. The number of soldiers, this is a famous one, the number of soldiers killed by horse kicks each year in corps in the Prussian cavalry. Okay, this example was made famous by a mathematician in the late 1800s or early 1900s. Did you know that Florence Nightingale was actually more of a statistician than a nurse? Okay, there's a lot of her work in statistics that was really important. The distribution of visual receptors in the retina of the human eye, the number of light bulbs that burn out in a certain amount of time, the number of viruses that can infect a cell in a cell culture. Those are all different examples that you could have. So, you're probably all dying to know how to work it out. Well, maybe you're actually not. But here we go. This is its formula. Okay, this is in red, it needs to be written down. The probability distribution. If X follows the Poisson distribution, we use a PO there, we just used a P, we would think we're talking about just general probability. And there's the parameter lambda. The probability that a random variable, big X, takes a specific value, little x, is e to the power of minus lambda times by lambda to the x over lambda factorial, and lambda can take any value from 0 upwards as long as it is an integer. Okay? I'm going to pause the video at that point and just hand out a handout to everybody. So, here we go. First example, we've got, on average, the number of demands for taxis to a taxi firm is 4 every half hour. Use a suitable model, state the reasons for your choice. To calculate the probabilities of no demand in 30 minutes, 1 demand in 1 hour, or fewer than 2 demands in 15 minutes. So, first of all, might be a blindingly obvious answer considering what we've been doing this morning. What model will we use?
I know you're all...
Throw them at somebody. So we will use the Poisson distribution. Okay, so we'll say X will follow the Poisson distribution with parameter lambda. But we have to give reasons for the choice. So what were the conditions for the Poisson? What was the first condition for the Poisson that you noted down a minute ago? Discrete. Okay? Is this discrete? This is looking for the number of demands for taxis. Well, yeah, it is going to be discrete. It can either be none, 1, 2, 3 or 4. Can't have 5.5 demands for taxi, doesn't make sense. Okay, what was the next condition then that we had? A constant rate. Okay, a constant rate which we call lambda. Okay, so what is our constant rate in this question? 4 per half hour, yeah, okay. 4 per half hour. So we could say now then that X will be Poisson and it's 4, and you can put in there sort of slash for per half hour. But lambda itself then will be the number 4. Okay, what else do we have in our conditions?
There is no fixed number of trials.
No fixed number of trials, yep. Technically that's not really a condition, it's something it isn't, which I just put in to compare it with the binomial, but yeah.
Fixed time period.
Fixed time period. our fixed time period is that half an hour that we are mentioning. Okay, so it does meet all of the conditions. Right, I'm just going to write down here, just so it's on the board, the formula we had earlier, the red box rule, if you want to think of it like that, for the Poisson distribution. Okay, just so we've got that in front of us. There we go. So, if we're going to answer this question, we have x follows the Poisson distribution 4 per half hour. This is a sort of notation you need to make sure you are writing down. I know we had it earlier on up there. And in part A of the question, they say what's the probability of no demand in 30 minutes? So we want the probability x equals 0. Yeah, okay. So that is literally a case now of just sticking 0 into that formula. So that will be e to the minus lambda, lambda to the power of x over x factorial. What does that reduce to? Which bits of that are really simple and straightforward?
Lambda to the x and x factorial.
Yeah. Lambda to the x here, anything in the power of 0 is 1. 0 factorial is 1. So actually, and that will always happen if you do any probability of it being 0, it's just the e to the minus lambda bit. So if we can get that as a decimal, .0183, yep, that's what I've got here, okay. 0.0183. Okay, so that was nice and straightforward for our first bit. Everybody happy about that before we go on? Right, okay. Part B, the question in words rather than notation or sort of a mixture here, was 1 demand in 1 hour. 1 demand in 1 hour. Okay, so any comments just before we move on?
We have to change lambda.
Yeah, we have to change lambda. The situation we had here was when we were dealing with a half an hour, and we defined x was to do with this, lambda 4 in half an hour. Well, we've got a different situation here in modelling, so we shouldn't really be using x anymore. We need to use a different letter.
Why can't we just use probability of x equals 0?
You can look at that in a minute and see. Okay, but the best thing is they're talking about hour-long periods, so we'll talk about y now, a different variable, Poisson. Well, what will its rate be per hour? 8. So okay, it's 8 per 1 hour. So we're dealing now with lambda being 8. It purely is a scaling up. And we want the probability that y equals 1. So the red box rule on the board will be e to the minus lambda, lambda to the y over y factorial. What does that one simplify be to before you bung it in your calculator? Yeah, the 1 factorial is 1, 8 to the power of 1 is 8, so that's e 8 to the minus 8. It's 8 times the size of the last answer. So you could just take that decimal if it's still on your calculator and times it. No, it's not, sorry, because I had a different thing there. If I'd used the same value of lambda, that would have been the case, but it's not, so forget that bit. What do we get?
1.0268.
Yeah, okay, I get here 0.0027. I'll come back to what you said a minute ago, James, a bit later. But I can just do it this way to start with. Part C was fewer than 2 demands in 15 minutes. What do we need to do first of all? Fewer than 2 demands in 15 minutes. Made a new, yeah. What letter do you want to use?
Z.
Z, okay. So Z is Poisson, and we are dealing now in 15-minute intervals. So what will the rate be for 15 minutes? 2. Yeah, 2 per 15 minutes. So now we've got lambda is 2. Okay. and they're asking for the probability of fewer than 2. So what is this about Z that I'm trying to work out? Fewer than 2.
1 and 0.
It will be 1 or 0, yeah, I'll write it down like that first of all. Strictly less than 2 means, well, the only options are it is Z or it is 1, because it can't be 2 because that's not strictly less than 2. So you have 2 probabilities to work out, red box rules up the top, work them out, add them together, get your answer. Okay.
For probabilities, is it okay to use standard form?
Yeah, it's not. Yes, normally you give your answer to 3 significant figures or something, but yeah, that wouldn't be a problem. Okay. Do we have numerical answer for the final thing?
0.5.
Yeah, that's what I've got here. It should now be on the board for you. Okay. So I'm just going to stop this video clip at this point. Okay, our second example. River water, or even river water, contains on average 500 bacteria per litre. So this is not a time one, this is actually a volume, which is like a measure of space. A large bucket of the water is collected, and after it's been stirred, a 1 centimetre cube sample is examined. So we've got to know here the link between centimetre cubes and litres. It'd be interesting to know whether you remember that from GCSE or not. Part A, find the probability of there being no bacteria in the sample. Part B, find the probability of there being at least 4 bacteria in the sample. Well, let's just deal with this units thing first of all. We know that the rate of the bacteria is 500 per litre. How many centimetre cubes make 1 litre? It is 1,000, yes. So it is 500 per 1,000 centimetre cubes. So what will our rate be for 1 centimetre cube? Yeah, I'm dividing by 1,000, divide that by 1,000 and you get that. So my rate, my expected rate here is going to be 0.5 bacteria on average per 1 centimetre cubed. So if we say here then that X is going to be the number of bacteria in 1 centimetre cubed, X follows Poisson distribution, and it's going to be 0.5 that is going to be our lambda value. So part A is what's the probability? There are none in it. Probability X is 0. Can anybody remember from the last example we did, what's the shortcut formula we can use if it's 0? Yeah, okay. So that is a shortcut formula you can use if you are doing the probability of it 0, because the other bits are just 1. You have something to the power of 0 and you have 1 factorial. So we're doing here e to the minus 0.5. Yeah, I got here 0.6065. Okay, so that's 0.607, 3 significant figures. Part B, the probability of at least 4. That's X is greater than or equal to 4. What probabilities do I need to add up to get this?
Unless you do 1 minus.
Let's just start with the first bit. Yeah, it would be infinite. What we are saying here is the probability it's 4 plus the probability it's 5 and so on forever. It would be an infinite series, which may not be the best thing for us really, having to do an infinite number of sums and add them up. Bit difficult to do in the time of an A-level exam. So your suggestion was?
If you do 1 minus probability y equals 3, y equals 2, y equals 1, y equals 0.
So what statement could I write down here involving a 4?
1 minus
Yeah, okay.
Yeah.
The exact opposite of greater than or equal to 4 is strictly less than 4, not including the 4. Okay? So, how many sums have we got to do now? Sort of in this bracket here, I've got to do x is 0, x is 1, x is 2, I'll write that one in, x is 3, thankfully I haven't got to do x is 4. Even to me, and probably to you, that's quite a lot of work, and whilst Nathan is tapping away happily on his calculator at the back, I'm now going to tell him there's absolutely no need to do that, because there are 4 tables of values that we can use for this, okay? Because if this number here had been much bigger than 4, it would have taken ages. So in this scenario, 2 things. The important thing here was, first of all, we changed it into a x is less than. Okay, that was really important. That was to avoid the infinite bit. And then what we are going to do here is we are going to use tables to help us. So either in the back of your textbook or in the green tables, you should find quite a few pages of cumulative Poisson probabilities. It's not a single page, it's quite a few of them. It's organised by what lambda is, and in our example, lambda was 0.5. So, can you find tables for lambda being 0.5? In the green book, I reckon it's on page 16. Okay, here we go. Lambda being 0.5 is here in the green book. It's giving me probabilities here for x values, and these are, well, what are they specific values, greater than, less than? What do you think, just from looking at them? They are less than or equal to, yeah. They are less than or equal to. And if you pass me the book a minute, please, does it actually say that at the top anywhere there? But they are less than or equal to values. It doesn't actually say it, but they are, okay? So the tables are less than or equal to. So we wanted the probability less than, strictly less than 4. What we need to do now is actually change that into a probability x is less than or equal to something. Less than or equal to 3, yeah. Okay? So we're actually going to make that change there, if we are going to use the tables. Change it into a less than or equal to. So if we find lambda is 0.5, which is here, go down to the row with a 3 on it, and I'm reading off 0.9982. 9982. So that should be the sum that we are doing, and if you do that sum, you get an answer of 0.0018. Okay, which is the answer to that question. Okay, so there are tables here. Why did the tables for 0.5 not bother going down below 6 when this row here does?
Because every probability below that point is just 1.
Well, every probability of each specific value there is going to be 0 to 4 significant places. It's going to be tiny. Yeah. It's one of those very skewed distributions. If you remember earlier, when lambda was very small, these are very skewed distributions here. So the probabilities, they do exist, but they are so small that they're not going to change. We are already basically at 1 to 4 significant figures here. So there's no point, if we're answering to 4 or 5 significant figures, there's no point in putting them in. That's why that stopped at that point. I'm going to stop the video clip at that point. Okay, in the third example, we've got the number of typing errors per 1,000 words is known to be, and you can read on there, on average, in the long run, 2.5. Part A, find the probability that in 4,000 words there will be at least 12 typing errors. And then part B, which often happens like this in a GCSE question, the typist types 3 essays, each of 4,000 words. Find the probability that each contains at least 12 typing errors. And we'll look at that bit in a minute. First off though, what is our lambda going to be? What is our rate going to be? Well, we know, to start off with, it's 2.5 errors per 1,000 words. These essays that they're doing are 4,000 words. Scale it up. How many errors would you expect? 10. Yep. So we'll have lambda is 10 per 4,000 words. Okay, didn't really need those brackets there, don't know why I wrote that down. So we will have x follows Poisson distribution 10, but we need to say what x is. It's the number of errors that we find, the number of spelling errors that we find per 4,000 words. So part A of the question, find the probability that the errors will be at least 12. To start with, what symbol goes in here between my x and my 12? It's going to be at least 12. Greater than or equal to, because 12 will do. We do not like that. We need to turn it round straight away into a less than or equal to. Put 12 in here. 11. Good. Okay. This one here included 12, so the opposite statement must not include 12. That must be 11 in there. So people who are already jumping to your tables, jump to your tables. You need to find lambda equals 10 bit of your tables. You need to find row 11 on your tables. What number are people getting from the tables for that? 0.6968 is correct. Is that what back row people have found? So the answer to our question is 1 minus 0.6968, which is 0.3032. Okay, nice little question, easy to do with the tables. Okay, so that was part A. Part B, the typist types 3 errors each 4,000 words. Now that links in with what we've done in part A. So how do we do part B? Qubits. Nice try? No. It's not saying the same thing happens exactly.
Oh, because it's not at least. What does it
You could just change it. Why would it not? Because each time there's a probability of 0.3032.
Correct point. Each time there's a probability of 0.3032 correct. Think back to something we said earlier on, which wasn't actually a condition, it was like a not condition.
It's not a fixed number of trials, but now there is a fixed number.
Brilliant. Now there is a fixed number of trials. Now we are looking at 3 essays. So what about part B? Binomial. Yes. Part B is binomial. With a fixed number of essays we are looking at. We are looking here at 3 essays. And our P, the probability of our success, well, success here is actually having at least 12 errors, but that is our P value. P will be 0.3032. So we are dealing with a new variable, let's call it y. Y is going to be binomial 3, 0.3032. And what is y in words? Y is
Number of essays with 12.
brilliant, yeah, thank you. It's the number of essays with at least 12 errors. And we want the probability that each contains at least 12 errors. So we want the probability that the number of essays with at least 12 errors is 3 out of 3. That is each of them containing it. Okay. So what's the formula for the binomial distribution? Who remembers it?
MCR, 1 to the R times 2 to the M on top.
Yep. Okay. There we go. Okay. So whack your numbers in, get an answer out, or do it on your graphics. N is 3, R is 3, P is what we had in the last question. Do I actually need to work out that last bracket?
You need to work out one of them.
Yeah, actually here, look, that's just going to be 1. That's just going to be 1 because it's going to be a power of 0 on it. So actually my answer is just coming from that bit there. So should have put a 3 there. Do we have an answer? Yeah, okay, then that is correct. You do often get one of these questions that starts off Poisson and then there's this subtle change in it and it ends up binomial. So just look out for that sort of thing happening, okay? Okay, the fourth example we're looking at the moment, again, slightly different scenario. The probability that a wrapped chocolate biscuit is double wrapped is 0.001, or in other words, 1 out of 100. Use a suitable approximation to find the probability that of the next 60 biscuits you will unwrap, none are double wrapped, and at least 2 are double wrapped. So let's just go back here first of all. What distribution models this situation to start with? If someone's fallen into the trap, someone speaks louder.
Binomial?
Why is this binomial at the moment?
Fixed number of trials.
Yeah. At the moment, this is binomial. We have a fixed number of biscuits. Okay? We have a constant probability they are double wrapped. So at the moment, this is binomial. So if x is the number of double wrapped biscuits, x is going to be binomial distributed 60, 0.01. Now, what is the question asking us? In part A, it's asking us the probability that x is 0, and in part B, it's asking us the probability that x is greater than or equal to 2. But the question is saying, using a suitable approximation. What approximation to the binomial have you learnt already? The normal. What approximation to the binomial do you think you're about to learn? Poisson. Yeah, okay. So new heading here is using the Poisson to approximate binomial probabilities. Why would, and you've got to put yourself in the place now of a 1950s statistician possibly, why would you not want to do binomial probabilities sometimes?
Because it's a thing to work out, because you've got to do massive powers and you've got to know your triangle.
Yeah, it's those factorials that are the killers, okay? Even when the first scientific calculator I had, if I wanted to work out the factorial of 69, which is the biggest one it would work out, it took it about 4 or 5 seconds. I don't know how quick yours are now, they probably just do it like that. But the old-fashioned scientific calculator I had, working out 65 factorial, took it a couple of seconds to do. And in 1950, when you didn't even have the calculators, these numbers just got massively big very quickly and were best avoided. So, just like when you approximated the binomial by the normal, your exam board has come up with some specific conditions that you need to learn, which is when you use it, and it's this. If x follows the binomial np, if n is greater than 50, in other words, it's quite a large thing, and in this question n was 60, so that's okay, and np is less than 5, then x follows the Poisson distribution. Oh, now, hang on a minute. What is our parameter for our Poisson distribution always? Lambda. Lambda is the what? The rate, which is effectively the mean. What is the mean of this distribution up here? NP, yeah. Okay, so there we go. And the approximation gets better, okay, as n increases, and so as n gets bigger, and as p gets smaller, the approximation gets better. Okay, so those are conditions that you really have to learn there for when you can use the Poisson to approximate the normal. So let's just see, does it work in this example? Should do, otherwise it's a stupid example. We had n was 60, p was 0.01. Well, n, yeah, is greater than 50, so we can be happy about that. np is 60 times by 0.01. What is 60 times by 0.01? 0.6, and that is definitely less than 5. So we can be happy about that as well, and we can go ahead and use our approximation. So we will say here that our x, which was previously off the top of the board, maybe no need for you to write it down, that we can approximate it as a Poisson NP, which we worked out to be 0.6. So part A of the question was approximating x is 0. What's the shortcut rule for x is 0? E to the minus lambda. Lambda is 0.6. E to the minus 0.6. Tell me that as a decimal. 0.5488. Okay, that's correct. Part B of that question was probability x is greater than or equal to 2. It was at least 2. What do I need to do then to that? Yeah, I need to turn that into a 1 minus the probability it's less than or equal to 1. Yeah, okay. The strict opposite of greater than or equal to 2 is less than or equal to 1. So I made that change there. Okay. So you could just do here, there's only two probabilities. Less than or equal to 1 is the probability it's equal to 0, or the probability it's equal to 1. Work those out, add them up, take them away from the beginning from 1, and you will get your answer. Some people may be there already, I don't know. Or did people decide not to do that? Front row here decided not to do that. They said that was too hard, let's use tables instead. Okay? If you use tables, you're looking for lambda equals 0.6 and you're looking for the row 1. What do you get from tables? 0.8781. That is the quickest way of doing it. So the answer you're looking for is 1 minus 0.8781, which gives you a final answer of 0.1219. Okay? Now, we have another 6 minutes left, so what we are going to do now is we are going to redo both of those parts A and B, but using the actual binomial, okay, just to see how close we are. So can we redo those now, not using the Poisson approximation, but redo using the good old-fashioned binomial. So we have a binomial 60, 0.01, part A, probability x is 0. That's really easy to do with the binomial. What calculation do you end up doing? Yep, you end up doing your q to the power of n minus r. And what do we get?
547.
Okay, yeah, that's the exact answer. The approximate answer that we had a minute ago was 0.5488. Well, that, you know, it's almost agreeing to three significant figures. So that's not too bad. It's better actually than the normal approximation to the binomial we looked at the other day. And part B was the probability that it was greater than or equal to 2, which you need to turn round and say it's probability that it's less than or equal to 2. You'll need the probability of it. Sorry, I got that wrong. That's less than or equal to 1, isn't it there? Less than or equal to 1. So you'll need the probability at 0, the probability at 1, add those together, take that result away from 1. This one here we've just worked out. This one here anybody have an exact figure for us? Go on.
0.1196 is what I got.
I've got 1212 here. Okay. So that's the exact answer. The approximation we had was 0.1219. So again, pretty close. Almost agreeing to 3 significant figures. Definitely agreeing to 2 significant figures. Okay. So this afternoon, in our next lesson, and I'll try and lump all of these videos together into one for YouTube later on, but this afternoon what we'll be doing is looking at what I hinted at earlier, is approximating the Poisson distribution by the normal distribution. That will sort of cover up all the teaching of this effectively, and then some time practicing these skills and setting you some homework which we'll all look forward to with great anticipation. So what we're looking at now is how the normal distribution can be used to approximate the Poisson distribution. You saw the diagram on this slide this morning, and we decided that when lambda was equal 10, which is the black curve on here, and we said really these should be a series of bars, but the black curve shape is very much like the normal distribution shape. So the key thing, if you can write down, is this. If x follows the Poisson distribution, then the mean will be lambda. As long as lambda is over 15, which is what your exam board says is a suitable condition, then x can be approximated by the normal distribution. Now, if I've given you something there, just go down to the pen at the moment, you should be able to pick up and realise there's a fact which I haven't given you so far, which you should be able to extract from this last line.
Can I just quickly ask, the way you keep saying the conditions and then followed by the exam board, is that because it's not necessarily founded on any basis? Or?
So yeah, I mean you may find that, yes, it may even find another A-level exam board say lambda has to be bigger than 20. Obviously the bigger the better, but your exam board is saying as long as it's bigger than 15, that will do. But yeah, you won't find all statisticians agreeing and say this, okay? So yeah, our exam board, we go with the 15. So, from this bit of information above the pen, is there anything else you now know about the Poisson distribution? Scott?
The mean is equal to the variance?
Yeah. Because for the normal distribution, this goes mean and variance. Well, we knew from this morning that the mean of the Poisson was lambda. Well, the variance of the Poisson is also lambda. Okay? So that's not actually written down somewhere, but it probably ought to be. So that the variance of the Poisson is also lambda. So the mean and the variance are equal to each other. Now, I did not show you where the PDF, where the formula, the red box rule caller, where you like came from. If you look at the textbook, it explains it. It goes into series and sums and things. You don't have to know where it comes from, although I hope some of you would like to know where it comes from, but in that case I'll just point you to the textbook. It has got it in the chapter. Right, why does it then talk here though about we need to use a continuity correction? Go on.
Because you're approximating something discrete using something continuous.
Spot on, yeah. We are approximating a discrete Poisson distribution by a continuous normal distribution, so we will need to use a continuity correction, and the larger lambda is, the better. Okay? So, what we're going to do now is go through a couple of examples based on that. So, is everybody finished with the red writing on there? Can I take that away? Okay. I think this is going to be example 5 then, if we carry on from this morning. Okay. We've got here, we're told that x follows the Poisson distribution with lambda being 22. And what we have to do is find the probability that x equals 18, part A, using the Poisson distribution. So in other words, doing it as an exact calculation. And part B will be using the normal approximation to it. And we'll just compare them and see how close they are and what's involved in doing it. Is our condition met? Is lambda bigger than 15? Yes, it is. So x will follow approximately the normal distribution. And what goes in this bracket? The mean and the variance, which are what values? Lambda and lambda, yeah. 22 and 22. Okay, the mean and the variance gives them that. Actually, I'm doing part B first, aren't I? By the look of it. Let's do part B first, because that's what I started doing. Okay, hope that's not going to upset anybody terribly. So, part B, I want the probability that x is equal to 18. Now, I would write it like this again, put a little PO here. Because if I'm dealing with a Poisson distribution, I want it to be 18. That was discrete. But I need to go for my continuity correction. How will I write that down using a normal distribution statement? That's right, between 17.5 and 18.5. Doesn't matter whether I put the extra bars on. We've said before that's going to be then the probability that it's less than 18.5. Get rid of that, get rid of that. Take away the probability that it's less than 17.5. You're all probably ahead of me. What should you be writing down now? What symbol comes on the next line? Phi, yeah, okay. X minus mu over the standard deviation. Don't forget square root that 22 on the bottom. Okay, so I've got the calculations on the board if you want to check. 0.0590. Everybody happy with that? Okay, and the exact one, what formula will it be? What will I have to do to get it exact? Somebody tell me the calculation. Okay, there we go. And has anybody got an answer for that one already?
10635.
Yeah, okay, 0.635. They do agree to one significant figure here in this example, which is not brilliant, I have to say. But as far as your exam board is concerned, lambda was sufficiently big for it to be okay. But that is the process you go through. So we're going to do one final example of this, and then we will have basically called it a day on the teaching of the Poisson. I'm going to get stuck into questions from the book. Looks like some people have started to do that already anyway. Okay, so the next example, I'm going to call it number 6, is a car hire firm that knows that in its fleet, so a car hire firm has a fleet of cars, and it knows that breakdowns occur at an average rate of 21 per week. assuming that the breakdowns are occur at a constant rate and independently of each other. So, assuming independent breakdowns. Do you think that's a fair assumption?
No.
Why not?
Because they might be cars with faults.
Or they might collide with each other, in which case you don't have two.
Okay. Fair enough. We're going to assume it anyway. But yeah, fair enough. Okay. So assuming independent breakdowns, one car breaking down doesn't impact on another one of their cars breaking down. What we want to do first of all is to find or calculate the probability of more than 27 breakdowns in a week. So, car hire firm, large fleet of cars for hire by the day. It's found the fleet suffers breakdowns at the rate of 21 per week. Assuming that breakdowns occur at a constant rate and independently of each other, calculate the probability in any 1 week more than 27 breakdowns will occur. Fruit gun for the first right answer. One thing to get right here is what value you are using for the continuity correction. We were interested in more than 27 breakdowns. What value shall I be using?
26.
That would allow me to include 27 if we said 26 and a half. 27 and a half, yeah. Okay, so it's going to be 27 and a half that goes in there. What's wrong with that, or why don't I like that? What have I got to do to that line?
1 minus.
Yep, that's a greater than, turn it into a 1 minus.
I assume that the pass up first.
Is the answer 0.0782?
It is. Well done.
Go fruit gun.
There we are, the enthusiasm of somebody for a fruit gum. And I'm going to stop filming at that point.